Hi, my name is Ashwani Kumar. In this video, we are going to see the Ugc Net December 2019 questions on the Unit 1, that is Semiconductors. So it is the first question we are going to see. And here the question is, in N-channel enhancement type MOSFET, a VGS, nothing but a gate to source voltage is increased beyond the threshold level, then what will happen to the drain current or else the density of free carriers? So like this, what happens, they are asking. So here, coming to the MOSFET, generally in the MOSFET we are having the two different types. One is the enhancement MOSFET and the second one is the depletion MOSFET. In the enhancement MOSFET, the channel is not there. We have to create the channel with the help of the gate to source voltage. And coming to the depletion MOSFET, the channel is already there at the time of manufacturing itself. If you want to stop the conduction, then we have to break the channel with the help of this gate to source voltage only. That means the gate to source voltage is acting like a control voltage for the entire conduction process of this MOSFET. And coming to the enhancement N-type MOSFET, so just the diagram can be drawn like this. And here he's asking the N-type enhancement MOSFET. That means the source and drain are the N-type and the substrate is the P-type. And it is, let's take it is a source and it is a drain and it is a gate, right? So it is a polysilicon and it is a silicon dioxide and it is a substrate, right? So whenever the P and N junction is there, then automatically the depletion layer will be formed. So this entire thing is a depletion layer. And now they are asking that when the gate to source voltage, nothing but gate to source voltage is increased beyond the threshold level. So coming to the N-type MOSFET, if the VGS is increased beyond the threshold voltage, what is the meaning of this threshold voltage is, the threshold voltage is the minimum voltage required to form the channel. That means whenever the positive gate voltage is applied, right, whenever the positive voltage is applied in between the gate and the source, then the minority charge carriers, nothing but electrons in this p-type substrate, will start attracting towards this gate. Then automatically this channel will break down, sorry, this depletion layer will break down and one channel will form. This channel is completely accumulated with the electrons due to this positively voltage at the gate terminal. So now these electrons will break down the depletion layer between the N-type and P-type here in this region, and now it is called as a channel. Whenever the channel is formed, then automatically what happens is that the charge carriers in the N-type starts flowing through the channel and from channel to the drain. That means the conduction process starts in the enhancement N-type MOSFET whenever the channel is formed. So the minimum positive voltage or the minimum gate to source voltage which forms the channel or which starts the conduction is nothing but a threshold voltage. That is the definition to this threshold voltage, and generally we are going to represent with V suffix th. So here the given question we can write in the mathematical format as V suffix gs, nothing but the gate to source voltage is greater than the VTH, nothing but the threshold voltage. Then what happens? So the first option is drain current will decrease. No, it is not the correct one, because here the drain current is increasing, but because the channel is created, then the charge carriers from the source starts flowing through the channel and from channel to the drain. That means the drain current will increases actually. Whenever the gate to source voltage is greater than the threshold voltage, then the drain current will increase. So the first option is wrong. And the density of the free carriers in induced channel will remains constant. Here what they told is that in the question, if the VGS is increased beyond the threshold voltage, then the density of the free carriers will not remain constant, but because the drain current will start increasing, so the density of free carriers or the electrons induced in the channel will not remain constant, and the density of the free carriers in induced channel will decrease. No, it will not decrease actually, and the density of the charge carriers or the free carriers in induced channel will increase, right? But because we are telling that whenever the VGS is greater than VTH, that means if the VGS is increased beyond the threshold voltage, then the drain current will increase. So the drain current increases means density of the free carriers induced in the channel will increase, right? So it is the correct option. And now coming to the second question, the band energy of silicon depends on temperature T and can be described as. So the band gap energy of the silicon, that means generally here the band gap is nothing but the gap which is formed in between the conduction band and the valency band. So whatever the gap is there, it is called as the energy band gap. Generally we will represent with the E suffix G, or else it is also called as a forbidden energy band gap. And generally in the intrinsic or else in the semiconductors, this energy band gap decreases with increase in temperature. So if the temperature is increased, then automatically the energy band gap will be decreases. Such type of property is based upon the negative temperature coefficient resistance, right? So negative temperature coefficient resistance means if the temperature is increases, then the resistance of the semiconductor decreases. That means the current increases. Current increases means the energy band gap is decreases with increase in the temperature. So these are all the internal links between the different parameters. So now here the correct equation for this Eg of T, that means energy band gap is a function of the temperature, is equal to 1.21, or else if you want to get the generalized expression, then we can write that Eg of T is equal to E naught minus beta into T, where E naught is nothing but the energy band gap of the semiconductor material at 0 degree kelvins, right? So here in the question they are asking for the silicon. So for the silicon at 0 degrees we can take it as a 1.21 electron volts minus beta. Beta is a material constant. For silicon the material constant is 3.60 into 10 power minus 4 into capital T, temperature. So now while coming to this equation, that is Eg of T is equal to, see if you observe, as I told that in the semiconductors, if the temperature is increasing, then the Eg decreases. If you observe this equation, if I'm increasing the temperature, see if I'm increasing the temperature, this term will increase. If this term is increases, then automatically Eg of T will decrease, right? So we can observe from this equation. So if you match up this equation here, the second option is perfectly matching with this one. So 1.21, which is nothing but energy band gap of the silicon at 0 degree kelvins, minus beta. The material constant of the silicon is 3.60 to 10 power minus 4 into temperature, that is capital T, right? So now while coming to the third question, in a semiconductor, the concentration of holes in valency band can be given as. So actually we need not to obtain the derivations for this one. You have to remember the standard equations. So if you consider any one energy band diagram, it is having the valency band, conduction band and forbidden energy band gap. So here based upon the temperature, so for example if you take a semiconductor with 0 kelvins, then we will be having the partially filled valency band and the partially filled conduction band will be there. So if we keep on increasing the what we call temperature, then the electrons will jump from valency band to conduction band, then automatically the holes will increase in the valency band and the electrons, free electrons, will increase in the conduction band. So the concentration of holes in the valency band depend upon the temperature, and the concentration of electrons in the conduction band is also depending upon the temperature, right? So as I already told that if you are increasing the temperature, the concentration of holes in valence band increase and the concentration of electrons in the valence band will decrease. And coming to the conduction band, if you keep on increasing the temperature, the concentration of free electrons will increase in the conduction band. So it is the case. And in the conduction band, we are not going to discuss about the holes. Okay, so keep that point in your mind. So electrons and holes concept will discuss only in the valence band only. We will not discuss about the holes in the conduction band. Okay, we will discuss only about the electrons in the conduction band, right? And now the concentration of holes in the valency band, that is P, is equal to Nv into e power minus of Ef minus Ev divided by kT. Here Nv is the number of energy states in the valency band and EF is the Fermi energy level, EV is the valence energy level. That means this one. So whatever the line is there here, so this line energy level is the EV, and whatever the line is there, this line energy level is the EC, right? So EV divided by K into T. K is the Boltzmann constant and T is the temperature. So this expression is matching with the first option. So the first option is the correct one. And apart from this one, if they ask you the concentration of electrons in the conduction band, then small n is equal to Nc into e power minus of Ec minus Ef divided by Kt. So it is the expression for the concentration of electrons in the conduction band. Okay, so remember both these two equations. And now while coming to this fourth question, so which of the following semiconductor devices are heterostructure devices? So heterostructure means we are using the two different materials to manufacture a device. So for example, if you are taking a diode, the entire diode is manufactured with the help of the intrinsic semiconductor, that is either silicon or germanium, and later we will dope the trivalents and the pentavalents, right? And so the BJT is also not the heterostructure device. Why? Because the BJT is also manufactured with the intrinsic semiconductor in the starting process. So the heterostructure means if in any one device the two sections are there, if let's take it is the gold, let's take it is the semiconductor, right? So gold is a metal, and let's take it is a silicon. So the silicon is a semiconductor. That means one metal and one semiconductor, both these two are clubbed together to form a device. Okay, so such type of structures is helpful for the Schottky diodes. Generally in the Schottky diodes or the heterostructure devices, we are using the gold and semiconductor junction, which is essentially helpful for the high frequency rectifier operations, right? So like that, here while coming to the HEMT is nothing but a high electron mobility transistor. So it is a heterostructure. And MOSFET is nothing but it is also a heterostructure. It is nothing but modulation doped field effect transistor. Okay. And coming to the UJT and gun diode, both these two are manufactured with the semiconductor materials. So that's why both these two are comes under the homostructure devices. So HEMT and MOSFET, both these two are the heterostructure devices. That means the A and B are the correct. So here the first option is the correct one. And now while coming to this fifth question, consider the following statements. So here they given that BJT, FET, UJT. So BJT is a current control device, and FET is a voltage control device, and UJT is a negative resistance device. FET and UJT can be used for the amplifications. So out of this ABCD, they are asking which statements are correct. So generally while coming to the BJT is called as a current control device. Why? Because based upon the base current, we are going to control the collector current. Why? Because we will say that IE is equal to IB plus IC, or else we can take that IEC is equal to beta into IB. That means in the common emitter configuration, the output current, nothing but a collector current, is depending upon the input current, that is base current, right? So that's why the BJT is a current control device. So it is correct with high input impedance, but actually the BJT is having the low input impedance, right? So that's why the BJTs are used to amplify the signals with low signals. Okay, it is used to amplify the low signals, or else less amplitude signals. Why? Because it is having the low input impedance. If you apply the high voltage signals, the BJTs cannot able to tolerate. It may damage, right? And coming to the next B, so it is a wrong option. So up to here it is correct, but high input impedance is a wrong one. And while coming to the FET, of course, high gain bandwidth means it depends upon the circuit and the capacitors we are connecting. And the B option is a FET is a voltage control device, exactly, because if you the based upon the gate to source voltage, the drain current will varies. So obviously the FET is a voltage control device with high input impedance and low gain bandwidth. So it is a correct high input impedance and low gain bandwidth. Why high input impedance? Because FETs are generally whatever the gate and Let's take it is a gate and it is source and it is drain. So here in this, if the gate to source voltage for any JFET, the gate to source voltage is reverse biased. So whenever the gate and source, these two terminals are reverse biased, then automatically the input impedance will be very high. So the B option is the correct one. And coming to the UJT, generally UJT is having the negative resistance. Why? Because if you observe the VI characteristics of the UJT, you will get like this. So wherever the part, if you increase the voltage but the current is decreasing, it is nothing but a negative resistance part. So the negative resistance is shown by the UJT. We can understand with respect to the VA characteristics of the unijunction transistor. So with the help of this negative resistance property, UJTs are helpful for the applications oscillators, right? So oscillator. So the C option is also correct one. And coming to the D option, FET and UJT can be used for amplification. It is a wrong one. FETs are used for the amplification and UJTs are useful for the oscillators, right? So that means here the B and C are correct. So the second option is the correct one.